we move on to certain examples of using Bernoulli theorem. The first example is that of a siphon. Siphon is something which you may have seen people who have run out of petrol do in order to transfer fuel from one tank to another without the aid of a pump. Let us simplify the problem as follows. We have a tank which contains a liquid, and we have a tube which is submerged inside one end and it is kept open at the other. So initially the entire tube is filled with the liquid. It is important for us to either keep the entire tube filled with liquid or to provide a suction or an initial flow. You might have seen this when people are trying to suck on one end of the tube in order to initiate the flow. But regardless of that, the siphon action can also be started when there is fluid throughout the tube. Let me call this point as B, let me call this point as A. So now let us uh, try to find out what the velocity at the exit point will be. So first things first, let us draw a reference point. Let this be the reference plane. So the reference plane gives us a reference point with respect to which we can write down the heights of the different points we are interested in. So if we consider an incompressible inviscid flow and a steady flow, we can apply Bernoulli's theorem between point A and B. So let me write down Bernoulli theorem between point A and point B. So PA by rho G plus 1 upon 2G VA square plus ZA is equal to PB upon rho G plus 1 upon 2G VB squared plus ZB, where this height is ZA and this height is ZB. And I have written down the Bernoulli theorem in its head form. So the head form is when the dimensions of all the terms in the Bernoulli equations are that of height or head. Often when you purchase pumps, the head of the pump will be given, that is the maximum height the pump can pump water to at zero flow rate. That is, it is the height at which fluid will just be able to come out of the pump, of the tube attached to the pump. Okay, so at A the cross section area is so large, the tank cross section area is quite large compared to the tube, and hence VA can be approximated to be 0, and therefore we have PA upon rho G plus ZA is equal to PB upon rho G plus ZB plus half VB square upon G, and thus we can write PA minus PB upon rho G plus ZA minus ZB is equal to 1 upon 2G VB squared. Now given that point A is also at the atmospheric pressure, because the surface of free water over here at this particular point is subjected to atmospheric pressure only. All the points at the interface are at atmospheric pressure, while point B is also discharging to the atmosphere, and therefore points A and points B are at atmospheric pressure. Okay, so you can imagine a streamline which connects the free surface, and if you apply Bernoulli theorem between these 2 points, the velocity is negligible at both these points, the altitude is same for both these points, and the pressure is therefore equal at both these points, neglecting surface tension effects, of course. So in that case, PA is equal to PB, this entire term vanishes, and therefore VB becomes square root of 2G ZA minus ZB is essentially the difference in height between the free surface of the water and the discharge point of the tube. Let me call this distance as h. So it becomes square root of 2gh. Now this gives us the exit velocity. By the continuity equation for all the other points in the tube, this is actually the velocity throughout the tube. So Vb is actually velocity throughout the tube, except at point A, because point A is like the inlet point and point A is sort of sucking in through an infinite area. So let us now consider a random point, let's call it C, which is at a certain height small h above the surface of the water. Let us apply Bernoulli theorem between points A and point C. So PA upon rho g plus VA square upon 2g plus ZA is equal to PC upon rho g plus VC square upon 2g plus ZC. Now PA is equal to the atmospheric pressure, and let us call it as P naught. So it is P naught upon rho g plus VA square. So VA can be neglected. It's not 0, but it can be neglected. So plus ZA minus ZC minus VC square upon 2g. And this is going to be equal to PC upon rho g. And this ZA minus ZC, so this is equal to minus H. So this becomes P naught upon rho g minus H and minus Vc square upon 2g. So Vb is also equal to Vc, and thus Vc square is going to be 2gh. So Vc square upon 2g is going to be simply capital H. So this particular term is going to be minus H, and this is equal to Pc upon rho g. And so this implies that at any point in the tube which is at a height small h, the pressure will be equal to the head due to pressure will be equal to the atmospheric head minus small h minus capital H. Okay, so we can therefore find out a point in the entire hydraulic circuit where the pressure will be minimum, and we can obviously see that the pressure will be minimum where this small h is equal to the largest distance from the interface. So the topmost point, let me call this point as D, and let me call this as HD. Therefore, with this convention, we can write PD upon rho g is equal to P naught upon rho g minus H minus HD, and this is essentially minus of H plus HD, which is essentially the difference in height between the discharge point and the highest point. Okay, this entire height is equal to capital H plus HD. So this brings us to the conclusion that the pressure in the hydraulic circuit is minimum at the highest point in the circuit, and the difference between that particular pressure and the atmospheric pressure is given by this particular equation. Now we come to a very useful conclusion from this. So this is the minimum pressure in the circuit. Two things can happen in this particular circuit. Actually, three things can happen. The first and most trivial possibility is nothing happens. The second possibility is this particular pressure, okay. So essentially, if I write it down in terms of pressure and not head, so this is the minimum pressure head. The minimum pressure will be actually PD is equal to P naught minus rho g H plus HD. This is the pressure equation. This is in terms of head. So what can happen is the pressure can fall below the vapor pressure. So the vapor pressure condition is when the pressure at the highest point falls below. So if PD falls below the vapor pressure, so if a pressure falls below the vapor pressure, it means that the fluid will begin to boil. So in the circuit, you will have local boiling. The other thing that can happen is the loss in pressure will be such that dissolved gases, will come out of the solution. Okay, a reduction in pressure leads to a loss in solubility, and that leads to removal of gases from the fluid, and that leads to bubbling. So this condition is called as cavitation. Actually, both this can be classified as cavitation, and it leads to formation of vapor bubbles at this point. Vapor bubbles or air bubbles at this point. Now, air or vapor is quite compressible, so during the flow, it can prevent the flow by merely allowing for compression of the air bubble. Okay, so allowing for a compression in the air bubble leads to a blocking of the flow. It will appear as if everything has stopped, but in reality, vapor bubble has formed. But if the vapor bubble starts to move, as it starts moving, at a certain point, the pressure will again begin to rise, because we know that the pressure over here will be atmospheric pressure minus this particular height as found from the equation. So the pressure again will increase, and once it exceeds the vapor pressure or it allows for a larger solubility of dissolved gases, the vapor bubble or the air bubble can again go back into the fluid by collapsing, and this collapsing process is often quite violent. And it may not sound much, but this violent collapse leads to erosion. It leads to local erosion, and if it is metal blades or some metal tube in question, it leads to a severe case of pitting, and it leads to a very poor performance. In the case of transport through pipes, one can often, while it's not relevant for the case of a siphon, when there is cavitation in a pipe, I don't know whether you've heard it or not, there is a certain ringing or a pinging in the pipe. It causes a audible ping, and that particular phenomenon is called as a water hammer. And a water hammer occurs when you suddenly close a valve in a running pipe. So there was some water which is flowing through a pipe, and you suddenly close this. The readjustment in pressure, because you're suddenly closing this, so all that pressure, all that velocity, inertia has to be transferred back, and it leads to an a creation of audible water hammer. That sudden pressure fluctuation leads to local cavitation, which eventually collapses back into the fluid. So let us try to put in some numbers in order to get a feel for cavitation, not cavitation, but siphon. So consider a tank like we have shown in the schematic. Let this be the tube. Okay. So let us consider that this particular lowest point and this particular point. So this total height is 5.5 meter. This particular height is 4 meter. This particular height is 1.5 meter. This particular height is also 1.5 meter. Okay, so the first question is, what is the velocity of oil through the siphon? So this is given as an oil. What is the velocity of oil? So we know that the velocity of oil will be equal to square root of 2gh, where h is this particular height, the distance of this exit, the discharge point from the surface of the water. So this will be equal to square root of 2g into 5.5. This comes out to be 10.39. Let me just verify it with the help of a calculator. The square root of 2 times 9.81 times 5.5. Yes, it is 10.39 meter per second. So the next question is, what is the pressure at point A? So pressure at point A is obviously, okay, so I have not defined what is point A. Point A is over here, and this is going to be point B. Okay, so point A. So what is the pressure at point A? Pressure at point A will be purely hydrostatic. So pressure at point A will be equal to the atmospheric pressure plus rho g times this particular height, which is given as 1.5 meter. So times 1.5. So this is 101,325 Pascal plus 10 to the power 3 times 9.81 times 1.5, and this comes out to be 116040 Pascal, essentially 116 kilopascal. So now the question is, what is the pressure at point B? So in order to find out the pressure at point B, we can make use of the Bernoulli theorem between these 2 points. So applying Bernoulli theorem between this point and this point, so point B is slightly inside the tube. Okay, point B is not at the surface of the tube, but it is inside the tube. And this information is quite useful because if it is at the surface of the tube, the velocity has to be equal to 0. But if it is inside the tube, then the velocity at point B will be equal to the velocity of discharge. This means if I apply Bernoulli theorem between points A and point B, so PA plus half rho VA square plus rho G ZA is equal to PB plus half rho VB square plus rho G ZB, and points A and B are given at the same level. Okay, they are given at the same level, so these two terms vanish. Moreover, PA is found out, so PA we know, VA is going to be approximately equal to 0, so this is 0, and this is going to be PB plus half rho VB square, and VB we've already found out to be 10 point, let's say 10.4 meters per second squared. So this entire thing is 10.4 meter per second whole squared, and so PB is 116 kilopascal minus half times 10.4 squared. So the kilo, so this will be in kilopascal. So the density 10 to the power 3, I'm sort of absorbing in this kilopascal. Just think about this. It's not a very tricky calculation. It's just that I've maintained kilo over here. Kilo is 10 to the power 3 and density is also 10 to the power 3. So this particular value comes out to be 116 minus half 10.4 squared is 61.92 kilopascal. So next, the question is, what is the pressure at the highest point? So the pressure at the highest point is over here, all right. So the pressure can be found out by applying the Bernoulli theorem between the surface and this point C, and we've already done that. So I'm just gonna directly give the result. So it's gonna be the pressure head at the highest point, if I call it C, is going to be the atmospheric pressure head minus the height of the highest point from the discharge point. So it is 5.5 meter from this level plus 1.5 meter from this level. So this total height is going to be 7 meters. So the loss in pressure in going from the atmospheric condition at the interface to the condition at the highest point is going to be -7. So this Pc will be P0 minus rho g times 7. So P0 is 101 kilopascal minus 7g. So this entire thing will be in kilopascal. I mean, I'll suggest you not to do this kind of a ad hoc calculation, but actually put in the exact values. I'm just doing it in order to save some time. So this comes out to be 32.33 kilopascal. I've used rho as 1000 by the way. Before anyone starts complaining that okay, I've told oil, but okay, in order to keep things simple, I've used rho as 1000 kg per meter cube. This should have been obvious when I did this particular hack calculation, but in fact, like I said, you should put in the exact numbers. Okay, yeah, so this is how you find out the pressure, and if this particular pressure drops below the uh, the vapor pressure of the particular liquid, then you are in trouble. Okay, so if you do this, if you keep the pressure throughout the circuit higher than the critical pressure, that the critical pressure in this case arises due to considerations of solubility of dissolved gases in a particular fluid or the vapor pressure of the fluid itself. So if you keep the pressure throughout the circuit higher than those critical pressures, you're in the green. Otherwise, you have some issues pertaining to cavitation. Remember this while designing any hydraulic circuit.